period of time, I've worked on everything from back-end services of various sorts, all the way to building an in-house database. And by that I mean actually the database engine, not building a database on top of MySQL. That, however, is a talk for a different time. But one of the things I've learned over the years is that I've learned a lot of things about system design and software design. But one of the problems that keeps cropping up is just making changes to the code base, right? So many of the problems that I encountered just came from trying to make simple changes, or sometimes not simple changes, to an existing code base. So why is that problematic, right? Well, the biggest problem, in my experience, is that some code changes somewhere, and then some other code breaks, right? And I see people nodding. I know you've experienced this, right? And I phrased it this way in the passive voice because it implies that it just happened, right? The code just changed, and then something else just broke, right? No one's at fault, right? But someone made the code change, right? The code just doesn't change by itself, right? So, right, what kind of breakage have I encountered, right? These are the three top categories of breakage that I've experienced in my life, right? I update a library dependency in one of my projects. Doesn't matter if it's JavaScript and NPM, Java, Maven, whatever. I bump a version on a dependency, and I think I'm good, right? It uses semantic versioning. I bump a minor number. It should be great. And then my project breaks, right? Again, I can see people nodding. I feel like if you've done this long enough, you've encountered this, right? Or I start refactoring my project, right? And I think this is going to go so fast. Except as I'm doing it, everything starts to break, right? Or I've made libraries. This was a mistake that I promised myself I'm never going to do again, right? I make a library, and I think it's so cool that other people use it. And then I make a change, and I start getting yelled at, right? Because their code broke. And actually, their code didn't break. I broke their code, right? They made a change, and I broke their code. It took me many years to learn to say, I broke your code, and I'm sorry, right? I've literally done all these things. And not just once. I've done these things more times than I should. I should know better by now, right? But the question is, why do these things break, right? I think a lot of us, if we worked, with software long enough, we start to get an intuitive sense, like, I think maybe this is a breaking change. And in fact, if you look at things like semantic versioning, which is supposed to save us, right? It just says, bump the major version if you make a breaking change. But what's a breaking change? Right? Like, how do you even characterize a breaking change? I mean, maybe you sort of know it when you see it, but not everyone does, right? Because otherwise my dependencies wouldn't break my project when I bump them. So what's the problem? And I've thought about this really hard for about 4 years, which coincidentally is the amount of time that I've built a database, which is a really large project and broke all the time, right? Some people in the audience know this because they've worked with me. So, what's the problem? And I've thought about it a lot, and I actually think the problem is that software development is actually a distributed system, right? I'm not talking about building a distributed system, like a distributed database or anything, or microservice architecture. I mean the actual process of writing the code and moving the code throughout these systems, right? It lives on your dev machine. You push and pull it from GitHub into different GitHub repos, goes through your build system, code gets transformed, gets pushed out into other deployment environments. Those are all replicas, right? And it's not that you're building a distributed system, right? And it's not that it is a distributed system in the traditional software sense, but it's a distributed system that's composed of people and computers. And that's still a system. And because the code, rather than data, is replicated in many places, it's distributed, right? And in fact, even your local build process, if you do modern software development, chances are you didn't write all the code by hand, you use libraries. And where do those libraries come from? They get pulled from a package repository on the internet, right? When your build system pulls that code, it's actually making a replica, right? It's the same sort of process that a distributed system undergoes when it exchanges data, right, with nodes, right, in the total distributed system. Right? And I actually have concluded after 4 years that a lot of the breakages, right, that I see in just day-to-day software development are remarkably similar to the breakages that I saw building, right, a distributed database system, which again, I'm going to preface this with, no one should ever do that. It's a terrible idea. Learn from my mistakes, right? So what does breakage look like in a distributed system, right? Well, first, in a distributed system, you have multiple systems that interact over a network. And networks are fundamentally unreliable, right? And the individual systems are fundamentally unreliable, right? The system can disappear, either because it crashed or because the section of the network it's connected to went away, right? These distributed systems, because the components of the distributed system are unreliable, in order to keep our data from disappearing, right, the data is replicated, it's copied, right, across all the nodes for resiliency. And you think, this is great. And the problem is, what happens if you want to make an update? Right? Well, the network's unreliable. If you talk to every system, you don't actually know if it successfully committed your update. And if you talk to one system and expect it to talk to all the others, the same problem applies. Right? At any given time, right, the data replicas on the different nodes in a distributed system can be different. Right? And the problem is not that they're different. The problem is if you can't figure out how to get the nodes to agree, right, on what data they should actually be storing. Right? And that's called inconsistency, and the real question is, how do we avoid it? Well, the number one thing, right, that a lot of people do when they get into a distributed system is they want to do things like locks, like you would use in multi-threaded programming. And this is done using this, it can be done, quotes around can, using what's called distributed coordination. And that's based around the idea that every replica holding data in the distributed system talks to each other. And they basically talk and say, well, this is what my state is, and this is what your state is, and obviously we're different. Now we have to decide how to reconcile that, right? And they decide basically by a majority vote. The algorithms are actually more complicated than that, but that's the basic idea. If you have 5, right, nodes in a distributed system, to get them to agree via consensus, it requires a majority vote of at least 3. Right? And if those 3 nodes if any 3 nodes can agree, then the other nodes in the system, right, the other 2, will go ahead and just overwrite whatever inconsistent data they had, right? This requires special algorithms, which are super hard to implement. No, I can't implement them. I've tried. But common ones that you may have heard of are things like Paxos, Zab, which is used inside a service called Zookeeper, and a more recent one is called RAF. It's used inside etcd and Consular services. If you do end up needing to use one of these, my only recommendation is use something off the shelf. Don't implement it yourself. It's a terrible idea. But the real problem with using coordination is that it's slow. And the reason is that every node has to talk to every other node, typically a bunch of times. And actually, this happens in the real world. If you've worked on a distributed team and you try to go, okay, we need to make a decision, and I alone can't make the decision. We need a group of people to make it, and we need a majority of them to agree, and you can't get them all in the same room, right? And you start playing phone or email tag, right? You've encountered the problem, right? That slowness in making that decision in the real world is mirrored in distributed systems in consensus algorithms, right? They typically happen much faster, but they still suffer the same things. Sometimes the systems can deadlock. If enough of the nodes are gone, you can't make forward progress, you can't make a decision without a majority, things like that. And so you can use coordination in distributed systems, but again, you take a performance hit. And that performance hit dominates over every other thing that you might try to do to speed it up, parallelism, things like that. And that's just from the fundamental communication overhead of talking, right, to every participant. So are there any alternatives, right? Well, slide is titled, alternatively, you could stay calm, right? What does calm mean? Calm is an acronym that came from some distributed systems research that came out in the last 10 years. And calm is an acronym that stands for consistency as logical monotonicity, right? Consistency is obviously the opposite of inconsistency, right? And calm is primarily a way of avoiding that slowness or that overhead of doing the sort of distributed consensus, right? And the calm theorem, which has a proof behind it, basically says that all those data replicas in a distributed system can remain or become consistent without any coordination service as long as the operations that you perform on the data are logically monotonic. What does that mean? Well, if you hearken back to, I don't know, maybe high school algebra, you may, in the dark corners of your mind, remember something that's, some discussion of monotonic functions. But the basic idea that we need to convey is that if we're talking about functions, the function a on the left here is monotonic, and that's because it always goes up. It could also stay the same, but a monotonic function, either the value has to go up or it has to stay the same. It can never go down. This function, because it goes down right here, is non-monotonic. Now, that's in algebra. That's with mathematical functions, right? What is logical monotonicity? What does logical monotonicity mean? And what does it mean in terms of code? So let's think about the code that we write, right? At a real simple level, a lot of the code that we write ends up turning into mappings between some named identifier and some other unit of code that we're going to call, right? I don't call memory location, right, 0xBAF3, right? I call a name, right, if I'm going to invoke a function, and the computer links or resolves that name to the actual location where the actual code that backs the function lives. So if we think of the code that we create as a set of pairs of identifiers that are paired with exactly one function or unit of code, we can turn this into a set, right? Or a map, right? A map of key to value is a set of key value pairs. Right, so if we have a mapping like this, if we have a mapping, and that mapping contains, right, the identifier foo maps onto this function, right, we can execute this code, right? Foo passing the arguments 1 and 2. This function isn't terribly interesting, right? But for this code, right, for this function called to execute, this mapping must exist in the computer, right? What happens if the mapping doesn't exist and I try to execute this? My execution breaks, right? And that seems obvious, right? We learned this early on, right? I tried to invoke something and it failed, right? Like, why did it fail? Because you didn't define the function. Well, that seems super obvious to me, right? This is like CS 101, whatever my first programming class was, right? But bear with me for a moment, right? What if we took this mapping and what if we said, I want to say that there is an additional mapping, right? From the identifier bar to this function, which is doing some math, I don't care what math it's doing, right? But after doing that assertion, right, these two mappings would exist inside the space of our code, right? And I did this modification and notice that the call to foo 1, 2 still works, right? Obviously it still works, right? So this change to the code didn't break it, right? And we should note that this change is monotonic, right? The set containing, right, that just contained the mapping of foo to its function, we added to that set a second mapping, bar, right? And intuitively we want to say, well, obviously it doesn't break because my code, which calls foo, didn't have anything to do with bar, right? But this property, right, is interesting because it maps onto the Coulomb theorem for distributed systems, right? If we add any new mapping, right, to the space of our code, right, it increases the size of the mapping, right? The set of these pairs increases, and therefore it's monotonic, right? So we have, right, this set that contains, right, two functions. What happens if we removed foo from it, right? Well, again, obviously we only have a set, we only have, right, a mapping of bar to its function. And now we've broken the code. Again, this seems obvious, right? But it's interesting, right? Because we've noticed that this is a removal. A removal from a set decreases the size of the set. If we plotted the size of a set on a graph, additions would always make it go up, and removals would make it go down. And that means that this change is logically non-monotonic, right? So generally we can say, right, that all non-monotonic changes to a code base are potentially breaking. But are all of them actually breaking, right? If we move bar from our mapping, right, calling foo right, that wouldn't break, obviously, right? And that's obvious to us because we could look at the mapping and we could look at the code that we're executing and go, obviously that change is safe, right? But what if we'd taken, right, those functions and distributed them out onto the internet as a library? Who has downloaded our library? The answer is we have no idea, right? And so once code has left our machine, if we don't want it to break for other people, we need to ensure that all of our changes are logically monotonic, right? Which implies, because this mapping not only applies for functions in whatever simplified language, right, I came up with for this, but the same thing is true of classes in Java or classes in Python, right? Or methods inside classes in Java, right? All of those things exist, right? We can describe them in terms of these sets, and we can talk about whether a change removes a function, right, or whether it adds it. And once the code's left our machine, right, the only thing that's safe is to never remove anything, right? If I never remove code from my library, right, it's extraordinarily unlikely that it's going to break. Of course, does it mean I can never remove anything? Because I have to say some of my happiest moments are when I do commits to GitHub and I see it go, you added 5 lines and you removed 20,000, right? It's like, it's the best feeling in the world, right? And the thing is, right, the Calm theorem doesn't say that you can never do non-monotonic things. What it actually says is you can only, if you want to avoid coordination, right, you can only do monotonic operations. But if you're willing to do some coordination, you can perform non-monotonic operations. In fact, to do them safely, you must do coordination. And if you think about this, right, like, how would you actually do this, right? I've distributed my library, and now I realize that this function that I wrote does terrible things, right? Terrible things could happen some percentage of the time if people invoke it. But maybe people already sort of depend on it, right? So we're in this area where it's sort of like, what's actually worse, right? Like what do you do? So you can do this. So for example, something that is safe to do, right, is that you need to communicate the fact that you plan to remove this, right? Deprecation markers are an addition, right? Deprecation markers don't change anything about the compatibility of your code, right? Deprecation markers are great because they're always safe to add, right? But once you've done that, you also need to talk to people, right? And you need to talk frequently because they won't hear you. And just like in distributed systems, you need to retry the communication several times because and you need to use broadcast channels, use emailing lists, use Slack, talk to all the people that you think might be potential users of code if you've distributed it off your machine. I speak from hard, bitter experience, right? And once you've done that, you can talk to them and you can actually try to go out and proactively try to identify, code that's potentially going to be broken by, the change that you're proposing. And you will probably miss some code. You will definitely miss some code. I've done this. In fact, I've done this within the last 6 months, and it's so hard, right? It requires so much communication, in-person communication. It's so slow, right? And this sucks. But again, personal responsibility, I'm the one who decided to remove it. So, right? Either I take responsibility for it and try to manage and coordinate this process, or I throw it over the wall and get popped for it and launch fireworks. I don't know. Right? And then, right, that's just the communication and the planning, right? Now you actually have to do the coordination, which means, and this is something else that's interesting, right, about the Calm theorem, is that it actually says, right, that monotonic changes, right, are actually safe to do in basically any order, right? Once they're received at all the locations, they will eventually converge to the same state. That's why it's safe, right, to do whatever monotonic changes you want. Non-monotonic changes are sort of like subtraction, right? Addition, right, is like a monotonic change. You can commute, right? can add 3 and 5, or 5 and 3, and you still get 8. But if you go 3 minus 5 and then flip them, right, or 3 minus 5 and flip it to 5 minus 3, that's not the same result. Non-monotonic operations in a distributed system have the same characteristic. They are very sensitive to order, right? And so that's something else you have to think about when you coordinate the change, right? You're probably going to have to make the removals. You're going to have to very carefully release the new code, right? And the reason for that is because fixes are going to have to be made, right, in those locations, but you can't actually make the fixes until the changed code, right? And you will definitely be yelled at, probably. Definitely will. I can already see some people have PTSD from doing this process, right? So again, we could try to do more sort of monotonic additions, right, to our code bases. But it just it starts to feel awkward, and I think this is from something that I think we're just addicted, right, to convenient names, right? Like, I want to type the shorter name. I want to type foo rather than foo underscore variant 3, right? But the truth is that like 4 years later, after the last project I worked on, I write names like this up front because I know that inevitably that one of these functions is probably going to be wrong, and I'm going to need to make a replacement, but I can't actually remove the old one. I have to add, right, the replacement and convince people to switch to it.
Have you ever done any Windows programming?
You know what? There is actually a slide for Windows, yes, on exactly that, right? Yeah, which I just discussed, right? Actually, this is a subtlety, right? We think about updating or replacing something. This is a subtlety that I think a lot of us miss, right? Often we're used to in computers to thinking about update in place, like registers in a computer, right? If the register is, quote, empty and I write something into it, that's roughly the same as overwriting something that's in the register. But the truth is that's actually sort of subtly different, right? Like an update or a replacement actually decomposes into first you remove logically the thing that's there, and then you add the new thing. So actually doing like straightforward replacements is also something that's subtly tricky, right? Unless that replacement is truly equivalent, right? As far as what the calling code expects from it, right? Update in place is potentially non-monotonic, which is another reason, right? Which is another reason to add a new function rather than replacing the existing one. And again, right, this happens in real life because, again, in the last 6 months, I've actually had to do this coordination process. And it was fairly well managed, and it still took 3 months. 3 months and about 4 people's time, right, to coordinate across all of Workiva. Or, right, you have the addition, right, you have the option. You can leave old code, and you can make, right, you can make the changes, right, rather than in place, you can make them as additions. And someone as the audience mentioned, right, like, this happens in real life, right? Here's the Stack Overflow question. What does EX stand for in Windows API function names? Answer, when Microsoft updates a function and the new function is incompatible with the old one, Microsoft continues to support the old function and the new one is given the same name with an EX suffix. And actually, unfortunately I couldn't find any examples handy, but you will find some functions in the Windows API that are function name underscore EX underscore EX underscore EX. Right? Right? And I mean, there's similar things. You'll find things in various parts of the Windows API, you know, like here it is. What's this ZW prefix? All the rest of these prefixes have namings, right? Like this one has no meaning, right? But the point is, ultimately, is that the names have meaning to us, but all the computer cares about is that they're unique, right? And in my experience, we can save ourselves a lot of future pain by just accepting slightly fugglier names. Now that doesn't just mean that you have to you know, shove everything into, say, a function name or a variable name or whatever. A lot of the languages we use have name spacing and module features. So for example, in Java, right, and I should get into this, right, in terms of refactoring and rewrites, you can consider using the namespace or package path, right? You can put that there, and the language supports allowing you to import things from there, and then you don't have to see the ugliness, or at least you don't have to see as much of the ugliness. Source of pain that I've encountered is refactoring. The number of times in my life that I've basically said, I'm going to do this refactoring. This code is awful. This project is awful. God damn it! I finally have a week of free time. I'm going to refactor this, and everything's going to be better. And then 6 months later, I finally give up, right? And I say, okay, this branch is dead. I just have to get rid of it, right? It's never going to merge. It's never going to work right. I get merge conflicts every time I update from master, and no one on my team is going to be able to review it, right? They don't understand any of this stuff, right? So part of this is, I actually think that a lot of us use, I myself in particular did this a lot. I use refactoring, right, to say I'm going to work on too much code. Like the scope is just too large, right? The term refactoring was originally meant to say, like, within this closed scope, like for example, within this function, right? I'm not going to change the parameters, the return type. I'm just going to refactor the internals of this function, the interior that's hidden, right? No one cares what the interior looks like as long as I maintain my function signature contract and my return type contract, right? And now, I've done this, I'm guilty of this. I've used refactor to mean covert rewrite. I'm just going to refactor this part of the code, just. And I'm more convinced now than I've ever been in my life that unless you're doing that very small refactoring, right, like the interior code inside a function, or the code inside like a very well-sealed class, right, that unless it's very small and very well contained, it has really well-defined boundaries, that you should never do. That's the only case where you should actually do that in place, right? Any more code than that, right? And I should also mention that even if you're refactoring the entire interior of a function, you have to be careful for things that are non-monotonic, right? Because the types of changes that are non-monotonic don't just apply to does the function exist or not with this name. And it also applies to how many parameters does the function take. But it also applies to the set of things that it accepts as input, right? If I take a function and it accepted all strings, right? And I add a condition in it that says, okay, now this function only takes, right, strings up to 100 characters and then throws an exception if the string is more than 100 characters. That's technically a breaking change, right? The only way it's not a breaking change is if you're extraordinarily lucky and no one's ever fed it, right, a string of more than 100 characters. So that's also something that you have to pay attention to. But in my experience, it follows that same sort of property, right? Before, right, we accepted all strings, and now we've removed from the set of all strings some strings that we're no longer going to accept. And that, again, is a sort of non-monotonic change. And to me, this way of thinking about it has been very useful for me because I've been able to think about and characterize, like, is this change likely to break, right? Again, function names, right, whether I remove a function name or replace it, right, is much easier to identify. But it's also useful to think in terms of, what does the function accept? But going back to refactoring in place, and if you want to do large refactors, which are really rewrites, it's been about 2 years now that I simply refuse to do in-place refactors on large chunks of code. It's never worked well, and I've actually seen people whose careers in companies have been derailed, right? Because what happens is that the refactoring drags on for months, right? And then finally someone says, you have to merge it now. You have to merge it now. And I've actually seen whole companies fly the entire development staff to a single location, and we all got to play QA and hunting down bugs while, right, we tried to force, right, the merge of this long-running refactor in. And, right, the people who were responsible for those refactors had huge reputational loss, right, within the company. And so this is just something that I generally refuse to do now. If I'm working in a language like Java that has packages or a language that has some sort of module system, what I do now is I just take, right, that whole section, whatever that top level package, right, that contains all the code that I might want to refactor, I just copy it, right, into a new package or module. And this seems simple. There is a little bit more work. Sometimes you have to go in and rename identifiers inside that code. But you can generally do that with search and replace, and then you do your rewriting, right, inside that new renamed module, right? And this, at first, right, when I first thought about doing this, it felt gross, right? I'm making these fugly package names. They're not very elegant. Now I've just I've duplicated, right, the size, right? And what it turns out is that it works, at least it worked for me, surprisingly well, right? I've been able to re-engineer huge subsystems and components, right, of projects this way. And it has a couple of advantages, right? One is that if you start it and it's not quite ready for testing or complete integration with the system, that's okay. I mean, you can still get agreement to merge it, right, with your master branch because it's not active. It's not used necessarily by the rest of the system, right? Or if you actually want to test it and you're trying to integrate this and actually getting to the point where you're trying to test it to see if you can actually use this module to replace the original one, you can flag it, right? You can find the code, right, that's the integration point, and you can add conditional flags. And if this sounds a lot like how people do feature flagging, I think it's effectively the same idea, right? And this works so well, right? Because one of the problems with long-running refactors is the refactor drags on and on and on. And unless you're completely diligent about merging in, because progress on the rest of the project doesn't stop while you're refactoring, right? Changes are coming in from other developers in the team or other parts of the company, and unless you are incredibly diligent about pulling all those in, and I become less and less diligent as the rate of merge conflicts increases, which it does with time, right? Eventually I give up, right? And because I end up in merge hell, right? But doing it this way, even if you're like, this isn't ready, right, to flip on in production, I can actually talk with people and say, all right, well, I'm just going to merge it into master, right? I can guarantee that that code is not going to get called. I can guarantee that code is not going to, affect, right, production stability, and I can actually get it into master, right? And now as I work on it, I'm folding in smaller and smaller, right, units of work, and I've done this about 5 times, right, in the last 4 years on extraordinarily major portions of our project. On the database engine project that I worked on, I used this technique to replace like the fundamental storage layer. I've used it to replace the query engine, and I've used it to replace the actual sort of distributed systems management, right, layer. And the only thing I was dissatisfied with was the code that this was replacing hung around for months longer than I had hoped, right? Like I didn't get to integrate it nearly as fast as I thought I would. But if I hadn't done it this way, I expect that I never would have integrated it at all.